Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be again looking at a small exercise where we want to find out the equilibrium position and linearize this system. So let's jump right in. We have a system with a mass that is able to move along this direction. We have a second mass attached. We have the angle phi, and phi, and we have a spring and a dampener. So we already see that this is a non-conservative system. We are also given the equations of motion. So this is what we have here. Now we want to find the equilibrium position, and we do that by setting q double dot and q dot to 0. And the q's that we are left with, these will be our q equilibrium. So our generalized coordinates q are s and phi. So we need to do do this one. So we get rid of that term because it has an s double dot. Here we have a phi double dot. Here we have again phi dot. And this is also 0. Here we have a double dot. This is gone. Here we have a double dot. And what we are left with is this one and this one. So already we see that S equilibrium is just S0. So direction, the length of the spring where it's not compressed and not in tension. Then for the angle phi, we have this equation, and we have again either 0 or pi. So you already see that if you have a sine, it's most of the time a pendulum, and it's either hanging from top to bottom or it is balancing upside down. Now we linearize. So let's get rid of this one so we can see better. Now we have to get the M, C, and K matrix. To get the M matrix, we have to do a partial derivative with q double dot. So let's see where we have a q double dot. We have it right there, and we have it right here, plus this part. And I forgot this one. So if we just look at the S first, at S double dot, we have this part, and we have this part that comes from here. Then for phi double dot, we have the cosine that is here and just the ml squared. Then for our C matrix, we have the D that is coming from this part. We have no S dot in the second, so that's why we have a 0. We have a q dot in the first, and that is right here. So that's where this term is coming from. And we have no q dot in the second equation of motion, so that's why we have a 0. To get the K matrix, we again do a partial derivative. Let's remove this, remove this. So if we just look at the S and the first equation, we only have this part. So that's why we have a C. This is a constant, so this is not, this is gone after the partial derivative, so we only have the C. If we look just at the S and the second equation of motion, we have nothing. Then if we just look at the Q, we have let's remove this as well. We have a Q right there, and we have a Q right here. And in the second term, we have a Q in this term and a Q in that term. So deriving those partially will get us these two terms. And now this is just a general K, C, and M matrix, but we need that at a equilibrium position, and we choose equilibrium 0, 0. So what we are left with is the mass matrix, the cosine turns to 1, the D matrix where sine turns to 0, and the K matrix where cosine and sine turns to 0, and we are only left with this part. Around equilibrium position 0 pi, we have the exact same thing, but the K matrix and the M matrix have a minus sign here and here, and this has a minus sign there. So in equilibrium position 1, we have a lambda that is k. The eigenvalues of the matrix K are positive, and the eigenvalues of D are also 0 or positive. So this position 1 is stable. If we look at position 2, we already see that the eigenvalues are negative. So they are larger than 0 and smaller than 0, negative. So this is not stable. I hope you see how easy it is to work with those equations if you just know what to do. That is, first get the equations of motion, then set the q double dots and q dots to 0, get your equilibrium position, do a partial derivative to get the m, k, and c matrix, evaluate those at the equilibrium position, and look at the eigenvalues of either k or k and c. I hope this video gave you a better understanding of the linearization of the systems. If you have any questions, feel free to ask them in the comments down below. I will do my best to answer them. Thank you very much, and I'll see you in the next video.